Hello, my name is Zachary Hedges, and this is my lab report for the Phys2212 Charged Tape Lab. The purpose of this lab was to observe the interactions between two charged pieces of tape to determine the charge on each piece. In this lab, we use the physics principles of Newton's second law, gravitational force, and the electric force. For my experiment, I found the magnitude of the charge to be 8.08 times 10 to the negative 9th coulombs, and the number of electrons lost on each tape to be 5.05 times 10 to the 10th electrons. Newton's second law states that force is equal to mass times acceleration. In this experiment, the net force is made up of the force of gravity and the electric force. Since we are observing when a piece of tape is not moving, we know that F net equals 0, and therefore the force of gravity is equal to the negative of the electric force. The force of gravity is found by multiplying mass times the gravitational constant of 9.81 meters per second squared. The electric force is obtained from this equation, where K is equal to 9 times 10 to the 9th Newton meters squared per coulomb squared. The conditions for this lab were that the length of the tape was 15 centimeters, the width of the tape was 2 centimeters. This means that the area of the tape was 0.003 meters squared. The length of an atom is 1 times 10 to the negative 10th, to the area of an atom is 1 times 10 to the negative 20th. Dividing gives us that the number of atoms is 3 times 10 to the 17th. Since the mass of tape is 1 gram per meter, the mass of our tape was 0.00015 kilograms. The system was tape B, and the surroundings were tape A and the Earth. Performing some calculations, I found that the charge of the tape was 8.08 times 10 to the negative 9th coulombs, and the number of electrons lost was 5.05 times 10 to the 10th electrons. For my computational model, I set my conditions to be the same, and I found the charge and number of electrons to be the same as I found in my calculations. Between the real-world experiment and the computer model, the assumptions and initial conditions were the same, as well as the fundamental physics principles used for calculations. So the calculation of forces, charge, and the lost electrons were all the same. The computer model showed predicted behavior compared to real-world experiment, which was observed behavior, and any discrepancies could have arisen from rounding differences. Potential sources of error included unequal charge distribution on the tapes, charges lost to handling the tapes, improper measurement, and a failure to account for other external forces. Assumptions we made include considering the tape was a point charge, that the charge was the same on both tapes, and that the mass of the tape was 1 gram per meter. If the charges of electrons and protons were inverted, our observations would have been the same. The tape would still attract other objects, as it would still induce dipoles. Electric fields would be in the opposite direction, though. It is important to handle the tapes as little as possible, as interaction with other objects, including hands, can lead to charges transferring. This transfer happens very quickly and reduces the magnitude of the charge in the tape, meaning that we can no longer assume the charges between the tapes is equal. The tapes will also have less repulsive force, which could skew measurements.